There are two types of beta decay, the kind that produces an electron and the kind that produces a positron. When we produce a positron, what's happening is that a proton is turning into a neutron. Then to conserve charge, a positron is also produced. Otherwise, we can have beta decay by having a neutron turn into a proton, and then an electron is produced in order to conserve charge. But actually, that's not all that happens. An additional third particle is produced called a neutrino. A neutrino has a very, very small mass and no charge. They're neutral particles, and they have a really, really tiny mass. We know that they have mass, but the mass is so tiny that no one has yet been able to measure it. Neutrinos mean little neutral ones, so they're very small, they have almost no mass, and they have no charge. They're neutral. So when we have beta decay reactions, we have a parent nucleus that can turn into a daughter nucleus plus an electron plus an antineutrino. So the little hat means it's an antineutrino instead of a neutrino. Or we can have a parent turn into a daughter plus a positron plus a neutrino. So if we have the case where an electron is produced, then that means one of the neutrons is turning into a proton. And so the number of protons increases. But the number of total particles stays the same. So we have the same total protons plus neutron. The type of element changes since we're gaining a proton. And then we also spit out the electron and the neutrino. The other kind of beta decay involves the production of a positron. In that case, we have a proton turning into a neutron, so one of the protons goes away. And we have a daughter nucleus with one less proton than before, but still the same mass number, plus a positron, plus a neutrino. So the neutrinos actually carry away some of the energy of this interaction. The third kind of radioactive decay that we want to talk about today is gamma decay. So in gamma decay, an excited nucleus emits a very high energy photon and becomes less excited. So because it's just emitting the photon and losing some of its energy, but not changing what kind of particle it is, the daughter nucleus is the same nucleus as the parent nucleus. So no particles are added to or subtracted from this nucleus. It remains the same, it's just not excited, and then the gamma ray photon is produced. So this gamma here indicates that we're talking about a photon. All these different kinds of radiation products can be measured using a device called a Geiger counter. So with a Geiger counter, some kind of ionizing radiation comes in. Ionizing means it has enough energy to knock electrons off of atoms. So the Geiger counter has a chamber that's filled with a gas. And once the ionizing radiation comes in from the radioactive decay, that ionizing radiation, be it an alpha particle or a positron or a gamma ray, it has enough energy to knock off an electron from one of the gas molecules. Now this chamber is charged. There is an anode, which is positively charged, running down through the middle, and then there's also a negative charge on the outside edge of the chamber. So when the particle becomes charged, it will be attracted to the negatively charged, because it's had an electron knocked off, so it will be attracted to the negatively charged outside of the chamber, whereas the anode will attract the electron that has been knocked off. So you have a little charge pulse, a little current pulse that this Geiger counter can detect, and it counts the number of those little current pulses, which correspond to a bit of ionizing radiation coming in and knocking an electron off the gas atom. So these are the big ideas that we looked at today. We looked at we looked at characteristic X-rays in the last lesson. In this lesson, we started with looking at lasers and how they work. Then we also looked at nuclei and how they can be described by the number of neutrons plus protons, the mass number, and also the number of protons. Then we looked at nuclear size, and we saw that it's very, very small. And we also looked at how atoms or nuclei of atoms are bound together with binding energy. When you put the bits together, some of the mass goes away and becomes the energy that holds the nucleus together. Then we also looked at radioactive decay, how the activity, the number of decays per second, is defined and how that can be found from the decay constant. And then we looked at expressions for seeing how the number of particles is reduced and also how the rate at which particles are decaying is reduced with time. And we also discussed the half-life. Then we looked at how in decay reactions the charge is conserved. The amount of charge is conserved for both sides of the reaction, and the atomic number, the total number of protons plus neutrons, is also conserved in radioactive decays. The decrease in mass in a radioactive decay becomes the kinetic energy of the products, and that's usually a significant amount of kinetic energy, so the products are moving very quickly.